Hello. Very few have joined now. It's 5 minutes. You're 5 minutes late. Okay, I'm going to present my screen. Can you see the screen? Okay. So yesterday we were discussing about interrupt handling in RTOS. What are the different methods for handling interrupts in RTOS? So there are three alternative systems for handling RTOS, and I had explained what the three system is in general. So now we have to go on to each method, each alternative method in detail. So the first method for handling interrupts was a direct call to ISR by the interrupting source and the ISR sending an ISR enter message ISM to the OS. So usually when an interrupt arrives, it will directly request the operating system, and the operating system will then suspend all the currently running process, and then the interrupt service routine will be handled. After running the interrupt service routine or after servicing the interrupt, it will return back to the task that has been suspended. That is what is normally happening. But in RTOS, there are three ways in which we can handle ISRs. And the first technique is the interrupting source can directly call the ISR instead of requesting the operating system. The hardware source, interrupt source directly calls the ISR, and then this ISR will start its execution. And before starting its execution, it will send a message to the RTOS, that is ISR enter message is sent to the RTOS to give a message to the RTOS that it has taken over the control of CPU. So, and after completing the ISR, it will return back by sending an exit message to the OS. And that is the first method. Now let us see how it is represented. What are the steps involved in the first method? There is direct call to ISR by an interrupting source and the interrupt service routine sending an ISR enter message, that is ISM, to the OS. So this is the diagrammatic representation, and here we have two blocks. These blocks are nothing but memory locations, and here we have shown two blocks of memory locations. And in the first block is the ISR routines. ISR routines in first block, and the next block it is the process that is corresponding to the function that is currently being executed by the OS. So some ith function of the OS is running, and here we have an ith interrupt ISR I, and this ith interrupt is stored in a particular memory block, and the OS function that is currently being executed is also in a particular memory block. So we have shown two blocks of memory here, and how on the right side I've shown the steps. Okay, is it clear? Hello, is it clear to you? Okay. So you have two memory blocks here. This is the first block where the ISR is running, and the bottommost block is the second block where a particular OS function is running. Say the ith function is running. Now the first step here is the interrupt source, the hardware interrupt source. Suppose it is the ith source. it is giving a direct call to the ISR. So this is the ISR block, and the first step is the interrupt service routine is directly calling the ISR. This arrow shows the direct call to ISR by the interrupt source I. So that is the first step. And once the interrupt source service routine is invoked by the interrupt source, this will send, the second step is, it will send a message to the OS. It is sending a message to the OS, and this message is the ISR start message. That is, it indicates that the interrupt service routine had taken control of the CPU and it has started its execution. So before starting, it will send a message that will be stored in a message queue. Here in the operating system, you have message queue for storing messages sent by the interrupt service routine. So that particular message, the start message, will be stored here, and that is the second step. The start message will be stored, sent to the OS, and it will be stored in this queue. And then it goes on execution. And finally, when it completes its execution, the third step, on return, it will send while during its execution, it can invoke other events, and these events, whichever events invoked by the interrupt service routine, will be stored in the message queue. So this is the message queue, and whenever an event occurs within the ISR, events means it can invoke other tasks. When the interrupt service routine is running, it can call other task, interrupt service task, IST, we call it as IST. So ISRs can invoke ISTs, and multiple ISTs can be invoked by a single ISR. All these ISTs, the request to process these ISTs will be stored in the message queue. There is a message queue here which stores the start message and all other events that has been invoked by the ISR. So this message queue, it can be a message queue or a mailbox into which these events are loaded, and these events will not the ISR will not get interrupted during its execution. Only after completion, the events that has been invoked by the ISR will be getting executed. So once an ISR is invoked, it will complete its execution, and if it wants to invoke any other task, all those requests will be stored in the message queue, and only after the completion of the ISR, these tasks that has been invoked by the ISR will be executed based on its priority. So the main point to note that while the ISR is running, it can send messages, and these messages will be stored in the message queue, and these messages can be any events which the ISR is invoking, and these events will be executed only after the completion of the ISR. So all these messages to invoke other tasks will be stored in the message queue, and after storing in the message queue, finally in the last step, the interrupt service routine will return back to the operating system. Once it is completed, once the ISR is complete, it will return back to the OS by sending an ISR exit message. So initially it will send an ISR start message, and at the end of its execution, it will send an ISR exit message to the OS. It is an indication to the OS that it has released the CPU and the OS can continue its execution. So this is the diagrammatic representation of the first method. Did you understand anything? Did you understand what I said? You want me to repeat it once more? Hello? Do you want me to repeat it once more? Okay. So this is the first mechanism we were discussing about how an interrupt request is serviced by an RTOS. So in this method, the interrupt source directly interrupts or directly calls the ISR. From the interrupt source, the interrupt request directly goes to the interrupt service routine. Normally, it goes to the operating system, but in this mechanism, it goes directly, the interrupt source the ISR request will directly go to the interrupt service routine. And this interrupt service routine is stored in a particular memory block, and this will start execution, and before execution it will send a message to the OS, because currently the OS was executing its functions. So, say OS was executing its ith function, and in between that this interrupt had arrived, and when the interrupt arrives, according to this mechanism, it will directly call the ISR, and since it needs CPU for execution, it will send a message to the OS, and that is the second step. It will send a message to the OS, and then that message is ISR start message. All messages sent by the interrupt service routine will be stored in a message queue, and this is the message queue. And here any message sent by the ISR will be stored in the message queue. So the first message sent is the ISR start message, and once the OS receives the ISR start message, it will suspend its execution, and this currently running task will be suspended, and the ISR will continue its execution. When the ISR continues, as along its execution, it can generate certain events, and all these events are nothing but invoking other functions. So these events will be stored in the message queue. There is a message queue, and in this message queue, all the events forked by the ISR will be stored, and these events, they won't be executed at that time. It will be executed only after the completion of the ISR. So in between its execution, before termination, if it has forked any processes, all these requests will be stored in the message queue. And finally, at the when it has completely executed, the last step is return, and during the return state, when the ISR has completely been executed, it will give a message to the OS, and that is ISR exit message will be sent to the OS. And this OS, when it gets the ISR exit message, it will resume the process that has been temporarily suspended, and it will continue its execution. And it will also check for the message queue. If there are any higher priority tasks in the message queue than the currently running task which has been suspended, then OS will execute those tasks which has higher priority in the message queue. So each time when the OS schedules a task, it will check for the priority of the task in the message queue, and if there is any task that has higher priority than the one that is to be executed, then those tasks will be scheduled for execution. So this is the first mechanism, and the steps are listed here. That is in step 1, that is the first step. So what happens on an interrupt? On an interrupt, the process running at the CPU is interrupted. Normally, the CPU is running one process, and in between that process, this ISR request has arrived. And so this will interrupt the currently running process. The interrupt will stop the currently running process, and the ISR corresponding to the source, the interrupt source, will start its execution. And the hardware source calls the ISR directly. In this case, there is a hardware source that calls the ISR directly in the first step. Now, in step 2, the ISR, once the ISR starts, whenever the ISR request arrives, it will start its execution, and before execution, it will send the ISR enter message to the OS. Since OS was executing some particular functionality at that moment, it will send a message to the OS, and this informs the OS that the ISR has taken control over the CPU. So since ISR wants CPU to begin its execution, it will send a message, ISR enter message to the OS to give an information that ISR has taken control over the CPU. And the message that this ISR enter message is stored in a memory location allotted for the OS messages. There is a message queue here, and all these messages will invoked by the ISR will be stored in the message queue. And that is the second step, that is giving a message to the OS. Then third is the ISR code will start its execution. So after sending a message to the OS, the ISR code will start its execution. And while executing, it can generate events. So ISR code starts execution, and during execution, ISR can post one or more outputs for the events, and these messages will be put into the mailbox or queue. Now this here we have shown the mailbox or the queue. All messages will come to the queue. And finally, return. The last step is after invoking all the messages, it will complete its execution, and on return from ISR, it will send an ISR exit message to the OS. So the last step, the fourth step, it will send an ISR exit message to the OS. And now the OS will check for the priority of tasks in the queue as well as the task that has been suspended. And if there are any higher priority tasks in the queue that is greater than the one that has been suspended, then it will start the event that has the highest, the task that has the highest priority. So that is what is written here. When ISR finishes, the interrupted task gets executed, or there is a rescheduling of task. The interrupted task is a task, the ith task. Either this ith task get executed, or it will check for the priority of the task in the queue, and then it will reschedule the task based on its priority. Okay, is it clear? Is it clear now? Okay, okay. So that was the first method. So here the interrupt source, hardware source, so the interrupt source directly calls the ISR. ISR sends an ISR enter message to the currently running process, and then it will get suspended. And during its execution, it will send many messages, and these messages all will be stored in the message queue. And after return from the ISR, it will send an ISR exit message to the OS, and the OS can either continue with the task that has been suspended, or it will check for the tasks in the message queue, and if there are any higher priority tasks, there is scheduling of tasks, and the highest priority task will be executed. That is the summary of this mechanism. Okay, now we are going on to the second method, that is the RTOS first interrupting on an interrupt. That is here, the RTOS is getting interrupted first. In this mechanism, the interrupt source is directly calling ISR. But in the second mechanism, the interrupt source will directly call the OS. The RTOS is getting interrupted when an interrupt arrives, and the RTOS then will call the ISR. And that is the second mechanism. Instead of directly executing the ISR, directly invoking the ISR by the interrupt source will now go to the OS, and the OS will invoke the ISR. That is the second mechanism. So RTOS first gets interrupted on an interrupt. When an interrupt arrives, the RTOS gets interrupted first, and then the RTOS will call the corresponding ISR. RTOS will call the ISR. So the steps are shown below. So before we show, here also we have two memory locations, two blocks of memory. The first block is for the interrupt service routine. Second block is for the currently running task of the OS. And also this block, it contains message queue for storing messages invoked by the interrupt service routine. So the first step is the interrupt source. Instead of directly going to the ISR, it will first give a request to the OS. And then there is the first step, interrupt source I directly invoking the OS, the first step. Next, in the second step, when the OS receives this interrupt request, it will save the context of the currently running process. Suppose the kth task has been running now. It will save the context of the kth process, that is the PCB, the process control block is saved for the kth process since it has been interrupted, and the OS has to return back to that kth process to continue execution. So it should save the contents of the kth process or the process control block of the kth process. And after saving, the third step, it will call the ISR. After saving the currently running process, it will call the ISR, and that's the third step. And so now it goes to ISR, and this ISR will start its execution. And when the ISR executes, again, just like what we had said before, it can invoke messages. And these messages will be stored in the message queue, or we call it as events or messages. All these events will come to the message queue or the event queue. And they won't be executed at that time. They will be executed only after the ISR has been completed. So while execution, it can fork messages or it can send messages. All messages will be stored in the message queue, and then finally it will return back. This is the fifth step. I haven't written five here. This is the fifth step. The last line going out of the ISR is the fifth step. So it will return back to this OS in the last step. And when it returns back, the OS will check whether the priority of the suspended process or the priority of the processes that has been in the message queue, that has been stored in the message queue, is greater. If some task inside this queue is greater, then it will run that particular task. Otherwise, it will continue with the kth task. So this is the mechanism. A second method for invoking interrupts. That is, the interrupt service routine first calls the RTOS, or first interrupts the RTOS, then RTOS saves the currently running process, and then it will call the ISR. ISR will start execution. During its execution, it can send messages. All messages will be stored in the message queue. These messages are nothing but invoking other processes, like we call it as interrupt service task. All these tasks will be stored in this message queue, and finally the interrupt will return back to the OS. And now the OS can decide whether to continue with the currently blocked process, that is gate task, or to the one that has the highest priority in the message queue. So again, there is scheduling of processes happening here, and based on scheduling algorithm, it will select one of the process. Is it clear? Did you understand the difference between the first and the two interrupt handling mechanisms? Hello? Can anyone say what is the difference between the first and the second mechanism? Hello? Can anyone just summarize? So the steps, I have said the steps in this figure, just go through the steps once again. So the first step is the OS first gets the hardware source call. Instead of the ISR, the OS gets the hardware source call from the interrupt source I, and this will interrupt the kth task. The currently running process in the by the operating system was the kth task, and once this hardware source call request arrives, it will interrupt the kth task, and that is first step. And the second step, the OS will save the contents of the kth task, currently running process K. OS saves the context of the currently running process K. And in the third step, it will call the corresponding ISR. OS calls the corresponding ISR, and during execution of the ISR, it can send events or messages into the mailbox. This is the mailbox, and during execution, it can send. Here I have shown only one, but it is a representation that it can fork any number of tasks. So during execution, ISR can post one or more events and messages into the mailbox of the OS. And and here, if there is a task J which has higher priority than task K that has been suspended, then it can be invoked. Based on priority, the task scheduling is done after the execution of the interrupt. Then the fifth step is return from ISR after retrieving the jth or kth task. There is one task J inside which has a higher priority, then the jth task will be executed. Otherwise, if K has the highest priority, then K will be executed. So on return from the ISR, either the jth task in the queue or the kth task that has been suspended will be executed. So on return from the ISR after retrieving the jth or kth task context based on priority. That is the last step. And OS initiates the ISR calls from priority based first in first out queue. There is a queue here, or a mailbox, as I said, is a first in first out queue. And a point to be noted here is that the ISR, that is the interrupt service routines, that is arriving on an interrupt. These ISRs have higher priorities than the task that it is forking. It will fork certain subtasks. The interrupt service routine will generate certain events to fork some subtasks, and these subtasks are called interrupt service task, or IST. So ISRs have higher priority. These ISRs have higher priorities than ISTs that are in this queue. Did you understand? Hello, did you understand? No response? Hello? Harita, did you understand what I said? Why no one is responding? Okay. So we were discussing about the second mechanism, and we had already okay, second mechanism. We have an example, the mobile PDA device, the mobile device which works on this second mechanism of interrupt handling. That is, you might have seen a device, a mobile device or a touchscreen device. Here the device has codes for ISR and they get executed by the RTOS. Now, whenever you touch a particular screen, that particular routine will be sent. That will be invoked. That is, if you're touching the using your PDA to touch a touch screen with a touch screen. When you touch the screen, this particular ISR touch screen will be initiated, and this will invoke a function called the ISR create function. This is a sample function named here, and this function, it will get executed, and finally when it completes its execution, it will return, the event handler will return back, and then when you touch the next point, next again when you are touching again, this function will be executed. So it is frequently interrupting the RTOS based on the touch you are giving. So that step is summarized here. This example was asked once for university exam. So I will explain it in the next class. Okay. Now take your attendance, please. Oh, it's still 9:30. Okay, I have 8 more minutes. So I'll explain that. So just see this example. So let us look at this example, the mobile PDA device. So here, each device, it has codes for ISR, and this gets executed by RTOS scheduling. And the scheduling mechanism followed is the second mechanism. And here, the ISR touch screen has been created by a function called the OS ISR create function. This function is invoked whenever the touch screen is activated, and the function interrupt connect, int connect, it connects the touch screen with a event handler called the ISR handler. So this connect function, it calls the ISR handler, and let us see what is happening with these functions in these 5 steps. In the first step, the user taps the screen at an icon or a menu, and the touch screen event occurs. So ISR touch screen is invoked whenever the user taps the screen or an icon on the menu on the touch screen. This ISR touch screen event occurs, and it is connected to the function OS ISR create function, and whenever the user touches the touch screen, this will say the contents of the currently running process. Suppose the system is running some other process at that time, it will save the contents of that currently running process, and the OS will send a signal on behalf of the ISR handler. The OS will invoke a signal, and this will initiate the ISR touchscreen function. ISR touchscreen function is invoked, and then the interrupt service thread, the IST touchscreen, is a sub-function of the ISR routine. IST is the touchscreen function. ISR is the interrupt that is arriving. Whenever this ISR touchscreen arrives, the IST touchscreen is invoked, and using a function called the OS event pen function. This event is continuously running in a loop, and whenever this ISR routine touchscreen arrives, this IST task is invoked, and when this IST task is invoked, it will service that particular routine, and then the IST, that is IST task, will start execution whenever the interrupt occurs, and it will execute as per the priority. There will be several tasks in the queue, and it will execute as per its priority. And if there are any pending ISTs, it will check for the priority, and it will execute the current touchscreen event. If it has higher priority than other tasks already in the queue. And so these are all certain functions, sample functions that are written. So on return, if the IST function starts execution, on return, it will send an ISR exit message. So these are all sample events. Just remember these 5 steps. Okay. So anyway, just go through the mechanisms. It is difficult for you to remember these functions. It's okay. You just need to write the mechanism. So now let us move on to the third mechanism. That is RTOS first interrupting on an interrupt, and then the RTOS initiates an ISR which calls another ISR. This another ISR is the one that has actually arrived. And here the RTOS, just like the second step, RTOS is getting interrupted. And when the RTOS is getting interrupted, it will not directly call the interrupt service routine. In the second mechanism, we found that whenever there is an interrupt, when an interrupt request is sent to the RTOS, it will save the content, and it will jump to the RTOS that has arrived, that has requested the service. And in this, the third mechanism, it will not directly jump to the ISR. Instead, it will initiate another ISR. This ISR will check for the priority of the currently arrived ISR as well as those that are in the message queue. And then if the currently arrived ISR has higher priority than all the tasks listed, then it will be serviced. So that is the third mechanism. So it happens in 2 levels. That is, first the RTOS will call, first the interrupt service routine will interrupt the RTOS. RTOS initiates an ISR. This ISR then invokes the routine that has ISR request that has arrived now based on priority. So that is what I said. Here we have 2 levels of ISR. One is a fast level ISR, another is the slow level ISR. So it happens in 2 levels, a fast level or FLISR or hardware interrupt ISR, and the second is a slow level ISR, SLISR or software interrupt ISR. So the third mechanism, once an interrupt request arrives, it is sent directly to the operating system, and the operating system will invoke an ISR, which in turn calls the ISR that has arrived if it has higher priority. Okay. So can anyone say the difference between the first three mechanisms? All the three mechanisms. We have only three mechanisms for interrupt handling. What is the first mechanism? Can anyone type in the chat box? Hello? So I'll just summarize it. Yes, webinar, direct call to ISR. That's the first mechanism. Instead of calling giving a request to RTOS, it will call the ISR directly. First, directly call ISR. Second, Shruti was saying something. Let me see. Okay, direct call to ISR. Second is the ISR request goes directly to the RTOS and the RTOS invokes the ISR. And third mechanism, again, the request goes to the RTOS as in the second mechanism. The ISR request goes to the RTOS, but RTOS will invoke another ISR, which will in turn invoke the ISR request that has currently arrived based on priority. Okay. So I'm happy that at least you understood this much. Is it clear? Okay, okay. Thank you, thank you. So see, take attendance, please. Number 1, 2, 5, 6, 7, 8, 9, 11. Okay, Abdul. Present 11, 12, 13, 14, 16, 17, 18, 20. Ramesh, 20. 20 absent. 22, 23, 24, 26, 27, number 27, okay, 28, 29, 30, 31, 32, 33, 30, number 3, Amal. Okay, thank you. So number 20, Ramesh is absent today.